We think we're significant, we think we matter in the grand scheme of things, but the reality of our cosmic address is so staggering that it challenges everything we believe about our place in existence. Today, we're going on a journey through scale that will leave you questioning not just how small we are, but how miraculous it is that we exist at all. Now let's begin. Our story starts with a number that seems almost impossible to comprehend. Our galaxy contains somewhere between 200 billion and 400 billion stars. That's not 200 million or 200,000, that's 200 billion with a B. To put this in perspective, if you counted one star every second without stopping, it would take you over 6,000 years just to count the lower estimate. And that's assuming you never sleep, never eat, never take a break. But stars are just the beginning. The Milky Way spans roughly 100,000 light-years from edge to edge. A light-year is the distance light travels in 1 year, about 9.5 trillion kilometers. Light, which can circle Earth 7.5 times in a single second, takes 100,000 years to cross our galaxy. If you could somehow travel at the speed of light, you'd spend your entire lifetime just getting halfway across our cosmic neighborhood. The European Space Agency's Gaia mission has revolutionized our understanding of our galactic home. Launched in 2013, this remarkable spacecraft has mapped over 1 billion stars with unprecedented precision, creating the most detailed, three-dimensional map of our galaxy ever produced. What Gaia revealed is both beautiful and humbling. We live in a vast spiral galaxy with 4 major arms, countless smaller structures, and a complexity that defies easy description. Our solar system sits about 26,000 light-years from the galactic center, roughly halfway between the center and the edge. We're located in what astronomers call the Orion Arm, a minor spiral arm that's really more of a spur connecting 2 major arms. Think of it as living in a cosmic suburb, not in the bustling downtown of the galactic center, not in the sparse countryside of the outer rim, but in a pleasant, middle-distance neighborhood. But even this suburban location contains wonders beyond imagination. Within just 50 light-years of our Sun, a tiny bubble in galactic terms, there are roughly 2,000 other star systems. Some host planets that might harbor life. Others are stellar graveyards containing white dwarfs, neutron stars, or black holes. A few are stellar nurseries where new suns are being born from collapsing clouds of gas and dust. The nearest star to our Sun is Proxima Centauri, located 4.2 light-years away. This might sound close in cosmic terms, but the scale is staggering. If Earth were the size of a marble, Proxima Centauri would be another marble located about 600 kilometers away. The space between stars is so vast that if you randomly fired a bullet in any direction from Earth, the chances of it hitting another star would be essentially zero, even if it traveled for billions of years. Yet despite these enormous distances, our galaxy is a dynamic, interconnected system. Stars orbit the galactic center in vast, sweeping paths that take hundreds of millions of years to complete. Our Sun has made roughly 20 trips around the galaxy since it formed 4.5 billion years ago. Each orbit is called a galactic year, and in that time, entire species have evolved and gone extinct on Earth. Continents have drifted across our planet's surface, and the very composition of our atmosphere has changed dramatically. If these cosmic mysteries give you chills like they give me, make sure to subscribe. I'm dropping mind-blowing space content every week that you won't find anywhere else. And smash that like button. It genuinely helps more curious minds discover these videos. Takes 2 seconds, makes all the difference. The Milky Way isn't just a collection of stars scattered randomly through space. It's a carefully orchestrated cosmic dance held together by gravity and shaped by forces we're only beginning to understand. Dark matter, which makes up roughly 85% of the galaxy's mass, provides the invisible scaffolding that gives our galaxy its structure. Without dark matter, the Milky Way would fly apart, its stars scattered into the cosmic void. Recent observations from the Hubble Space Telescope and ground-based observatories have revealed that our galaxy is far from alone. We're part of what astronomers call the Local Group, a collection of more than 80 galaxies bound together by gravity. The largest member is the Andromeda Galaxy, containing roughly 1 trillion stars and located 2.5 million light-years away. In about 4.5 billion years, Andromeda and the Milky Way will collide and merge, creating a new, larger galaxy that astronomers have playfully nicknamed Milkomeda. But let's zoom back in to appreciate just how small we are within our own galaxy. Earth orbits an average-sized star in an unremarkable part of a minor spiral arm. Our entire solar system, including the orbit of Neptune, spans about 60 astronomical units. An astronomical unit is the distance from Earth to the Sun, roughly 150 million kilometers. 60 astronomical units sounds like a lot until you realize that the nearest star is over 270,000 astronomical units away. The scale becomes even more mind-boggling when we consider that our solar system is just one of potentially hundreds of billions of planetary systems in the Milky Way. The Kepler Space Telescope, during its 9-year mission, discovered over 4,000 confirmed exoplanets by observing just a tiny patch of sky. Extrapolating from these observations, astronomers estimate that nearly every star in our galaxy hosts at least one planet, and roughly 20% of Sun-like stars have Earth-sized planets in their habitable zones. This means there could be tens of billions of potentially habitable worlds in our galaxy alone. Some might harbor simple microbial life, others could host complex ecosystems, and a few might even be home to intelligent civilizations. Yet the distances between these worlds are so vast that communication, let alone travel, presents challenges that push the boundaries of physics and imagination. The James Webb Space Telescope has begun to reveal the chemical compositions of exoplanet atmospheres, searching for biosignatures that might indicate the presence of life. Water vapor, oxygen, methane, and other molecules can tell us whether distant worlds might be habitable or even inhabited. We're living in an extraordinary time when we're beginning to answer one of humanity's most profound questions. Are we alone in the universe? But even as we search for life elsewhere, it's worth reflecting on how remarkable our own existence is. The elements that make up our bodies, carbon, oxygen, nitrogen, calcium, iron, were forged in the nuclear furnaces of massive stars that lived and died billions of years ago. When these stars exploded as supernovae, they scattered these elements throughout the galaxy, enriching the gas clouds from which new stars and planets would eventually form. Carl Sagan famously said we are made of star stuff, and this isn't just poetic language, it's literal truth. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was created in stellar cores under temperatures and pressures that dwarf anything we can imagine. We are, quite literally, the universe becoming aware of itself. The Milky Way's spiral structure plays a crucial role in making life possible. The spiral arms are regions of enhanced star formation where gas clouds are compressed and triggered to collapse into new stars, but they're also regions of increased radiation and stellar violence. Our solar system's location between spiral arms provides a relatively safe haven, protected from the worst of the galaxy's more energetic phenomena, while still benefiting from the heavy elements produced by stellar nucleosynthesis. This concept, known as the galactic habitable zone, suggests that life might be most likely to arise in the galaxy's suburbs where we happen to live. Too close to the galactic center, and radiation from the supermassive black hole and frequent supernovae would sterilize planets. Too far out, and there wouldn't be enough heavy elements to form rocky planets and complex chemistry. We exist in a cosmic Goldilocks zone, not too hot, not too cold, but just right for life to flourish. The supermassive black hole at our galaxy's center, known as Sagittarius A star, weighs roughly 4 million times as much as our Sun. This cosmic monster, located 26,000 light-years away, is so massive that it influences the orbits of stars throughout the galaxy. The Event Horizon Telescope captured the first image of this black hole in 2022, revealing the shadow of the event horizon against the glowing accretion disk of superheated gas spiraling into oblivion. Despite its fearsome reputation, Sagittarius A star is currently quite peaceful. It's not actively feeding on large amounts of material, so it doesn't produce the brilliant jets and intense radiation that characterize active galactic nuclei. This quiescence is another factor that makes our galaxy hospitable to life. In more active galaxies, the central black hole can outshine all the stars combined, bathing the entire galaxy in lethal radiation. The structure of our galaxy reveals itself in layers of increasing complexity the more we study it. What appears as a simple spiral from artistic renderings is actually a barred spiral galaxy, with a central bar-shaped structure extending roughly 27,000 light-years from end to end. This bar rotates as a solid body, completing one rotation every 230 million years, and it plays a crucial role in funneling gas toward the galactic center and triggering star formation in the spiral arms. The Spitzer Space Telescope's infrared observations revealed this bar structure clearly for the first time in 2005, showing us that our galaxy is more complex than we previously imagined. The bar connects to the spiral arms at specific points, creating a pattern that astronomers describe as resembling a cosmic pinwheel with a handle. We're living inside this vast, rotating structure, completely unaware of its motion on human timescales. Our galaxy also has a thick disk and a thin disk, each with different stellar populations and characteristics. The thin disk, where we reside, contains younger stars, gas, and dust, while the thick disk hosts older stars with different chemical compositions. Above and below these disks extends the galactic halo, a roughly spherical region containing ancient globular clusters, individual halo stars, and vast amounts of dark matter. Globular clusters are among the most spectacular objects in our galaxy. Dense collections of hundreds of thousands to millions of stars packed into regions just a few dozen light-years across. These stellar cities are relics from the galaxy's youth, formed when the Milky Way was still assembling from smaller building blocks. The Hubble Space Telescope has revealed that some globular clusters contain multiple generations of stars, suggesting a complex formation history that astronomers are still working to understand. The scale of these globular clusters puts our cosmic insignificance into sharp perspective. Omega Centauri, the largest globular cluster visible from Earth, contains roughly 10 million stars packed into a sphere about 230 light-years across. If Earth orbited a star in the center of Omega Centauri, our night sky would contain thousands of stars brighter than Venus, and there would be no true darkness, just a perpetual twilight illuminated by countless suns. But even Omega Centauri is just one of roughly 150 globular clusters orbiting our galaxy. These ancient stellar cities follow highly elliptical orbits that carry them far above and below the galactic disk before plunging back through it. They're like cosmic time capsules, preserving information about the conditions that existed when our galaxy was young and the universe was less than 1 billion years old. The discovery of stellar streams has revealed that our galaxy is constantly growing through the accretion of smaller galaxies. The Gaia mission has identified numerous streams of stars that were torn from disrupted dwarf galaxies as they fell into the Milky Way's gravitational embrace. The Sagittarius stream, created by the ongoing destruction of the Sagittarius dwarf galaxy, wraps around our galaxy multiple times like cosmic ribbons. These galactic mergers might sound violent, but they're actually gentle processes that unfold over hundreds of millions of years. When a small galaxy falls into the Milky Way, tidal forces gradually strip away its stars, creating long streams that eventually become part of our galaxy's halo. It's cosmic recycling on the grandest scale, with our galaxy growing larger and more massive by consuming its smaller neighbors. The Milky Way's magnetic field adds another layer of complexity to our galactic home. This field, though incredibly weak by terrestrial standards, threads through the entire galaxy and plays crucial roles in star formation, cosmic ray propagation, and the behavior of interstellar gas. Radio telescopes can map this magnetic field by observing polarized emission from cosmic ray electrons spiraling around magnetic field lines. Recent observations have revealed that our galaxy's magnetic field has a complex, twisted structure that follows the spiral arms and extends far into the galactic halo. This field helps confine cosmic rays, high-energy particles accelerated by supernova explosions and other violent processes, keeping them trapped within the galaxy for millions of years before they eventually escape into intergalactic space. The interstellar medium, the gas and dust between stars, makes up roughly 10 to 15% of our galaxy's normal matter. This might sound like empty space, but it's actually a complex ecosystem of hot and cold phases, with dense molecular clouds where stars form connected by networks of warm, diffuse gas. The average density is incredibly low, about 1 atom per cubic centimeter, but spread across the galaxy's vast volume, this adds up to billions of solar masses of material. Molecular clouds are the stellar nurseries where new stars are born. These dark, cold regions can span hundreds of light years and contain enough material to form thousands of stars. The Eagle Nebula, made famous by Hubble's Pillars of Creation image, is just one example of these stellar birthplaces. Within these towering columns of gas and dust, gravity is slowly winning the battle against thermal pressure, causing the material to collapse and fragment into the dense cores that will become new stars. The process of star formation connects us directly to the galaxy's chemical evolution. Each generation of stars enriches the interstellar medium with heavier elements produced through nuclear fusion in stellar cores. The first stars in the universe contained only hydrogen and helium, but successive generations have gradually increased the metallicity, the abundance of elements heavier than helium, throughout the galaxy. Our Sun is a third-generation star, formed from material that had already been processed through at least 2 previous generations of stellar evolution. This is why Earth contains the heavy elements necessary for rocky planet formation and complex chemistry. We exist because billions of years of stellar evolution have enriched our corner of the galaxy with the ingredients for life. The scale of stellar evolution becomes apparent when we consider that massive stars live fast and die young, exploding as supernovae after just a few million years, while low-mass red dwarf stars can shine for trillions of years, longer than the current age of the universe. The most massive stars in our galaxy burn through their nuclear fuel so quickly that they barely have time to move from their birthplaces before exploding, while the smallest stars will outlive every other object in the galaxy. Type T2 supernovae, the explosions of massive stars, are among the most energetic events in the galaxy. A single supernova can briefly outshine the entire galaxy, releasing more energy in seconds than our Sun will produce over its entire 10 billion-year lifetime. These explosions not only enrich the interstellar medium with heavy elements, but also trigger the formation of new stars by compressing nearby gas clouds. The supernova rate in our galaxy is roughly 1 explosion every 50 years, though though most occur in regions hidden by dust and gas. The last supernova visible to the naked eye from Earth was Kepler's supernova in 1604, observed by Johannes Kepler and visible in broad daylight for weeks. The next galactic supernova could happen tomorrow or not for another century. Stellar evolution operates on timescales that dwarf human experience. Speaking of cosmic scales that dwarf our galaxy, if you're fascinated by how small we are within the Milky Way, you should definitely check out my video on how big is the universe compared to the Milky Way. It explores scales so vast that our entire galaxy becomes just a tiny speck in an ocean of cosmic structures. The journey from our galactic neighborhood to the observable universe will completely reshape your understanding of cosmic scale. The link is in the description and pinned on the comments. Neutron stars represent some of the most extreme objects in our galaxy. These stellar remnants pack more mass than our Sun into a sphere just 20 kilometers across, creating gravitational fields so intense that a teaspoon of neutron star material would weigh as much as Mount Everest. The fastest spinning neutron star known rotates 716 times per second, its surface moving at roughly 24% the speed of light. Pulsars, rapidly spinning neutron stars that emit beams of radiation like cosmic lighthouses, serve as precise cosmic clocks. The Crab pulsar, formed in the supernova observed by Chinese astronomers in 1054, spins 30 times per second with such regularity that it rivals atomic clocks in precision. These stellar timekeepers help astronomers study everything from stellar evolution to the fundamental properties of matter under extreme conditions. Black holes scattered throughout our galaxy represent the ultimate endpoints of stellar evolution for the most massive stars. Stellar mass black holes, typically weighing between 5 and 50 times our Sun's mass, are invisible except when they're actively feeding on material from a companion star. The hot gas spiraling into a black hole can reach temperatures of millions of degrees, glowing brilliantly in X-rays before disappearing forever beyond the event horizon. The galaxy contains an estimated 100 million stellar mass black holes, most of them invisible and undetectable with current technology. They drift through space like cosmic ghosts, revealing their presence only through their gravitational effects on nearby objects. The nearest known black hole, Gaia BH1, lies just 1,500 light-years away, practically next door in galactic terms. Binary star systems make up roughly half of all stars in our galaxy, adding another layer of complexity to stellar evolution. When massive stars in binary systems explode as supernovae, they can kick their companions to tremendous speeds, creating hypervelocity stars that travel fast enough to escape the galaxy entirely. Some of these stellar refugees have been detected racing through space at speeds exceeding 1,000 kilometers per second. The chemical composition of stars throughout the galaxy tells the story of cosmic evolution. Astronomers can determine a star's age, birthplace, and formation history by analyzing the elements in its spectrum. The APOG survey, part of the Sloan Digital Sky Survey, has analyzed the chemistry of hundreds of thousands of stars, revealing that our galaxy's disk formed through a complex process of gas accretion, star formation, and chemical enrichment over billions of years. Population I stars, like our Sun, formed relatively recently from gas enriched by previous generations of stellar evolution. Population II stars are older and more metal-poor, formed when the galaxy was younger and less chemically evolved. The oldest stars in our galaxy, found primarily in the halo and globular clusters, are nearly as old as the universe itself, providing windows into cosmic conditions more than 13 billion years ago. The Galactic Coordinate System helps astronomers navigate our vast stellar neighborhood. Galactic longitude measures position around the galactic center, while galactic latitude measures distance above or below the galactic plane. Our Sun sits at the origin of this coordinate system, making us the center of our own cosmic map, even as we orbit the true galactic center. The motion of our solar system through the galaxy reveals just how dynamic our cosmic neighborhood really is. We're not sitting still in space, we're racing through the galaxy at roughly 230 kilometers per second, completing one orbit around the galactic center every 225 to 250 million years. This galactic year represents a fundamental timescale in cosmic evolution, during which entire ecosystems rise and fall on Earth. But our motion is even more complex than simple orbital motion. The solar system also oscillates up and down through the galactic plane like a cosmic yo-yo, crossing through the disk roughly every 33 million years. Some scientists have proposed that these passages through the denser galactic plane might trigger increased comet impacts on Earth, potentially contributing to mass extinction events, though this remains a topic of active research and debate. The local standard of rest provides astronomers with a reference frame for measuring stellar motions within our galactic neighborhood. This represents the average motion of stars in our vicinity around the galactic center. Relative to this standard, our Sun has a peculiar velocity. It's moving roughly 25 kilometers per second faster than average in the direction of the constellation Hercules, while also moving slightly inward toward the galactic center and upward out of the galactic plane. This peculiar motion might seem insignificant, but it tells us about our solar system's history. We might have formed in a different part of the galaxy and migrated to our current location through gravitational interactions with spiral arms, molecular clouds, or other stellar systems. Stellar migration is a common process that can transport stars across vast distances over cosmic time, mixing stellar populations and redistributing chemical elements throughout the galaxy. The concept of galactic habitable zones extends beyond simple distance from the galactic center. Astronomers have identified several factors that influence a region's suitability for life: metallicity levels sufficient for rocky planet formation, supernova rates low enough to avoid sterilizing radiation, and stellar densities that minimize disruptive gravitational encounters. Our location in the galaxy appears to satisfy all these criteria remarkably well. The metallicity gradient in our galaxy shows how chemical enrichment varies with distance from the center. Inner regions of the galaxy are more metal-rich due to higher rates of star formation and supernova enrichment, while outer regions remain more pristine. Our solar system's location places us in a zone with just the right metallicity for forming terrestrial planets while avoiding the radiation hazards of the inner galaxy. Spiral density waves provide the theoretical framework for understanding how our galaxy maintains its spiral structure over billions of years. These waves propagate through the galactic disk like traffic jams on a cosmic highway, compressing gas and triggering star formation as they pass. The spiral arms we see are not permanent structures, but rather temporary enhancements in stellar density that rotate around the galaxy at a different speed than the stars themselves. Our solar system's relationship to these spiral arms has changed over time. We currently reside in the Orion Arm, but we've passed through major spiral arms multiple times during our galactic history. Each passage might have exposed Earth to increased radiation from young, massive stars and supernovae, potentially influencing the evolution of life on our planet. The local bubble represents our immediate galactic neighborhood, a cavity in the interstellar medium roughly 300 light-years across, carved out by supernova explosions over the past 10 to 20 million years. We're currently traveling through this relatively empty region, which has a density about 10 times lower than the average interstellar medium. This cosmic void might help protect our solar system from some of the galaxy's more hostile environments. Recent observations from the E-Rosetta X-ray telescope have mapped the hot gas filling the local bubble, revealing its complex three-dimensional structure. This bubble connects to other cavities and tunnels in the interstellar medium, creating a network of low-density regions that astronomers call the local cavity. We're essentially living inside a cosmic soap bubble blown by ancient stellar explosions. The discovery of the local fluff, a small interstellar cloud that our solar system has been passing through for the past 60,000 years, reminds us that space isn't truly empty. This cloud has a density of about 300 atoms per cubic centimeter and a temperature of roughly 7,000 Kelvin. While incredibly tenuous by terrestrial standards, it's dense enough to interact with our solar system's magnetic field and influence the heliosphere. The heliosphere, the bubble of charged particles blown out by our sun's solar wind, extends far beyond the orbit of Pluto and serves as our first line of defense against galactic cosmic rays. The Voyager spacecraft have crossed the heliopause, the boundary where the solar wind meets the interstellar medium, providing our first direct measurements of conditions in nearby interstellar space. These measurements revealed that the local fluff has a magnetic field strength of roughly 3 microgauss, about 6 times stronger than previously expected. This interstellar magnetic field helps deflect some galactic cosmic rays, providing additional protection for life in our solar system. We're not just passengers in the galaxy, we're actively interacting with our cosmic environment in ways we're only beginning to understand. The age structure of stellar populations in our galactic neighborhood tells the story of star formation history over billions of years. The oldest stars in the solar vicinity formed roughly 12 billion years ago when the galaxy was young and metal-poor. Successive generations of stars show increasing metallicity, documenting the gradual chemical enrichment of our local environment. White dwarf stars serve as cosmic fossils, preserving information about stellar evolution and galactic chemical history. These stellar remnants cool slowly over billions of years, and their surface compositions reflect the interior chemistry of their progenitor stars. The white dwarf luminosity function, the number of white dwarfs at different brightness levels, provides an independent measure of the age of our galactic neighborhood. The coolest white dwarfs in our vicinity have surface temperatures of just 3,000 to 4,000 Kelvin, indicating ages of 10 to 12 billion years. These ancient stellar remnants formed when the galaxy was much younger, providing direct evidence for the antiquity of stellar populations in our cosmic neighborhood. We're surrounded by the cooling embers of stars that died billions of years before our sun was born. Brown dwarfs, the failed stars that never achieved sustained nuclear fusion, populate the space between stellar systems in numbers that might rival true stars. These substellar objects are incredibly difficult to detect due to their faintness, but infrared surveys have revealed hundreds within just a few dozen light-years of Earth. The nearest brown dwarf, Lumen 16, lies just 6.5 light-years away, closer than many true stars. The brown dwarf population provides insights into the low-mass end of star formation and the transition between stars and planets. Some brown dwarfs host planetary systems, while others wander through space as isolated objects. The total number of brown dwarfs in our galaxy might exceed the number of stars, making them a significant but largely invisible component of galactic structure. Rogue planets, worlds ejected from their birth systems through gravitational interactions, might be even more numerous than brown dwarfs. Theoretical models suggest there could be billions of these orphaned worlds drifting through our galaxy, invisible except when they occasionally pass in front of background stars and create gravitational microlensing events. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct the first comprehensive survey of rogue planets in our galaxy. These observations might reveal a vast population of wandering worlds, some of which could retain enough internal heat to support subsurface oceans and potentially even life, despite their isolation from stellar energy. The concept of panspermia, the idea that life might spread between worlds through natural processes, becomes more plausible when we consider the vast numbers of rogue planets and the occasional close encounters between stellar systems. While still speculative, some scientists propose that life might be a galactic phenomenon, spreading from world to world over cosmic timescales through meteorite impacts and gravitational interactions. Our understanding of stellar distances has evolved dramatically over the past century. The parallax method, which measures the tiny apparent shifts in stellar positions as Earth orbits the Sun, provides direct geometric distances to nearby stars. The Gaia mission has extended parallax measurements to over 1 billion stars, creating the most accurate three-dimensional map of our galactic neighborhood ever produced. Hipparcos, Gaia's predecessor, revolutionized our understanding of stellar distances and motions in the 1990s. The mission revealed that many stars previously thought to be nearby were actually much more distant, while others were closer than expected. These improved distance measurements forced astronomers to revise their understanding of stellar properties and galactic structure. The Gaia data has revealed that stellar motions in our galaxy are far more complex than simple circular orbits around the galactic center. Stars follow elliptical paths that can carry them far above and below the galactic plane, while gravitational interactions with spiral arms and molecular clouds constantly perturb their orbits. The galaxy is a dynamic, ever-changing system where nothing follows a perfectly predictable path. Moving groups and stellar associations provide evidence for the common origins of stars that formed together but have since dispersed throughout the galaxy. The Ursa Major moving group, which includes several bright stars in the Big Dipper, consists of stars that formed together roughly 300 million years ago and are now scattered across hundreds of light-years of space. These stellar families help astronomers understand how star-forming regions evolve and disperse over time. Young stellar associations, like the Scorpius-Centaurus association, contain hot, massive stars that will live only a few million years, while older moving groups consist primarily of longer-lived, lower-mass stars that preserve the chemical signatures of their birth environments. The local association, which includes our Sun, consists of young stars within roughly 300 light-years that share similar ages and motions. This suggests that our solar system might have formed as part of a larger star-forming event roughly 4.5 billion years ago, though the other members of our birth cluster have long since dispersed throughout the galaxy. Stellar streams from disrupted clusters provide another window into galactic dynamics and star formation history. The Hyades stream, created by the gradual dispersal of the Hyades star cluster, extends across hundreds of light-years and contains stars with ages and chemical compositions similar to the main cluster. These streams show how gravitational interactions slowly tear apart even the most tightly bound stellar groups. The discovery of hypervelocity stars, objects moving fast enough to escape the galaxy entirely, has revealed new aspects of galactic dynamics. These stellar refugees, traveling at speeds exceeding 500 kilometers per second, are thought to be created through gravitational interactions with the supermassive black hole at the galactic center or through supernova explosions in binary systems. Some hypervelocity stars appear to have originated in the Andromeda galaxy, suggesting that galactic interactions can fling stars across intergalactic distances. These stellar messengers carry information about conditions in distant galaxies and provide unique laboratories for studying stellar evolution in extreme environments. The vertical structure of our galaxy adds yet another dimension to our cosmic insignificance. While we often think of the Milky Way as a flat disk, it actually has substantial thickness, roughly 1,000 light-years for the thin disk where we reside, and about 3,000 light-years for the thick disk of older stars. Above and below these disks extends the galactic halo, a roughly spherical region that reaches out to perhaps 300,000 light-years from the galactic center. Our solar system sits almost exactly in the galactic plane, giving us an edge-on view of the disk that appears as the Milky Way band across our night sky. If we lived in the galactic halo, we'd see our galaxy face on as a magnificent spiral structure spanning much of the sky. Instead, we're embedded within the disk, like trying to see the shape of a forest while standing among the trees. The thick disk contains older stars with different chemical compositions and kinematics compared to thin disk stars like our Sun. These stellar populations formed during different epochs of galactic evolution when the galaxy was more turbulent and gas-rich. The thick disk stars have higher velocities and more eccentric orbits, suggesting they formed during a period of intense merger activity early in the galaxy's history. Stellar kinematics, the study of how stars move, reveals the complex gravitational forces shaping our galaxy. Stars don't simply orbit the galactic center in perfect circles. Instead, they follow rosette-shaped paths that carry them closer to and farther from the center over time. These epicyclic motions create the spiral density waves that maintain our galaxy's spiral structure. The velocity dispersion of stars increases with age, a phenomenon known as kinematic heating. Young stars, like our Sun, have relatively circular orbits and low random velocities, while older stars have been scattered into more eccentric paths through gravitational encounters with molecular clouds, spiral arms, and other stellar systems. This gradual heating process provides another clock for measuring stellar ages. Our Sun's galactic orbit isn't perfectly circular either. We're currently moving slightly faster than the circular velocity at our distance from the galactic center, placing us on a mildly eccentric orbit that carries us between roughly 24,000 and 28,000 light-years from the center. This orbital variation exposes our solar system to different galactic environments over time. The concept of galactic seasons emerges from our oscillatory motion through the galactic plane. As we move up and down through the disk every 33 million years, we experience different densities of stars, gas, and dust. Some researchers have proposed that these galactic seasons might influence Earth's climate and biological evolution, though the evidence remains inconclusive. Molecular clouds represent some of the most massive structures in our galactic neighborhood. These dark, cold regions can contain hundreds of thousands of solar masses of material spread across hundreds of light years. The Orion Molecular Cloud Complex, visible to the naked eye as the Sword of Orion, is one of the nearest star-forming regions at roughly 1,500 light-years distance. Within these molecular clouds, gravity battles against turbulence and magnetic fields to create the dense cores that will eventually collapse into new stars. The process is incredibly inefficient. Only about 1 to 2% of a molecular cloud's mass typically ends up in stars, while the rest is dispersed by stellar winds and radiation from the newly formed stars. The Eagle Nebula, located roughly 7,000 light-years away, provides a spectacular example of ongoing star formation. The famous Pillars of Creation, captured in stunning detail by the Hubble Space Telescope, show dense columns of gas and dust being sculpted by radiation from nearby massive stars. Within these pillars, new stars are forming even as the surrounding material is being eroded away. Star formation rates vary dramatically across the galaxy. The central regions experience intense starbursts triggered by gas inflows and gravitational instabilities, while the outer regions form stars at much more leisurely rates. Our location in the galactic suburbs provides a relatively stable environment where star formation proceeds at a steady, sustainable pace. The initial mass function describes the relative numbers of stars born with different masses. For every massive star that forms, hundreds of low-mass stars are created. This means that while massive stars dominate the light output and chemical enrichment of the galaxy, the vast majority of stars are small, cool red dwarfs that can shine for trillions of years. Red dwarf stars make up roughly 75% of all stars in our galaxy, yet they're so faint that none are visible to the naked eye from Earth. Proxima Centauri, the nearest star to our Sun, is a red dwarf with a mass just 12% that of our Sun. These stellar lightweights will outlive every other type of star, continuing to shine long after the universe has grown cold and dark. The habitable zones around red dwarf stars are much closer to the star than Earth's orbit around the Sun. Planets in these zones would be tidally locked, with one side permanently facing the star and the other in eternal darkness. Despite these challenges, red dwarf systems might host the majority of habitable planets in our galaxy, simply because these stars are so numerous and long-lived. Recent discoveries by the Transiting Exoplanet Survey satellite have revealed that planetary systems are incredibly common throughout our galactic neighborhood. Nearly every star appears to host at least one planet, and many systems contain multiple worlds. The diversity of planetary architectures is staggering, from hot Jupiters orbiting closer to their stars than Mercury orbits our Sun, to super-Earths with no analogue in our solar system. The Kepler Space Telescope's observations of a small patch of sky revealed over 4,000 confirmed exoplanets, suggesting that our galaxy contains hundreds of billions of worlds. Some of these planets orbit in the habitable zones of their stars, where liquid water could exist on their surfaces. The number of potentially habitable worlds in our galaxy might exceed the number of people who have ever lived on Earth. Yet despite this abundance of worlds, the distances between them remain staggering. The nearest confirmed exoplanet, Proxima Centauri b, lies 4.2 light-years away. With current technology, it would take tens of thousands of years to reach this world. The vast scales of our galaxy make interstellar travel one of the greatest challenges facing any spacefaring civilization. The search for extraterrestrial intelligence continues to scan our galactic neighborhood for signs of technological civilizations. Radio telescopes listen for artificial signals, while optical searches look for laser pulses or other technosignatures. The breakthrough Listen project monitors millions of stars for any hint of intelligent activity, yet the galaxy remains mysteriously quiet. This apparent silence, known as the Fermi paradox, raises profound questions about our place in the galaxy. If planets are common and life arises readily, where is everybody? Perhaps intelligence is rarer than we think, or maybe advanced civilizations tend to destroy themselves or transcend the need for interstellar communication. The answer to this puzzle will fundamentally change our understanding of our cosmic significance. The galactic chemical evolution tells the story of how heavy elements spread throughout our stellar neighborhood. Each generation of stars enriches the interstellar medium with elements forged in stellar cores and supernova explosions. Oxygen, carbon, silicon, and iron gradually accumulate over billions of years, enabling the formation of rocky planets and complex chemistry. Our solar system formed from material that had been processed through multiple generations of stellar evolution. The abundance patterns of elements in our Sun reflect the cumulative nucleosynthesis history of our galactic region. We can read this chemical story in meteorites, which preserve pristine samples of the solar nebula from which our planetary system condensed. Isotope ratios provide even more detailed information about galactic chemical evolution. Different stellar processes produce characteristic isotopic signatures, allowing astronomers to trace the contributions of various types of stars to the solar system's composition. The presence of short-lived radioactive isotopes in early solar system materials suggests that a nearby supernova might have triggered the collapse of the molecular cloud that formed our Sun. The local group of galaxies provides the broader context for our galactic home. This gravitationally bound collection of over 80 galaxies spans roughly 10 million light-years and contains three major spiral galaxies, the Milky Way, Andromeda, and the smaller Triangulum galaxy. The rest are dwarf galaxies with masses ranging from millions to billions of solar masses. Dark matter dominates the mass budget of the local group, making up roughly 85% of the total mass. This invisible component provides the gravitational scaffolding that holds galaxy groups together and determines their large-scale structure. Without dark matter, the local group would have dispersed long ago, its member galaxies scattered by cosmic expansion. The Magellanic Clouds, our galaxy's two largest satellite galaxies, are currently being disrupted by tidal forces as they orbit the Milky Way. The large Magellanic Cloud contains roughly 10 billion stars, while the small Magellanic Cloud has about 3 billion. These irregular galaxies are connected by a stream of gas and stars called the Magellanic Stream, which extends across more than 100 degrees of sky. Recent observations suggest that the Magellanic Clouds might be on their first passage around our galaxy rather than long-term satellites. Their high velocities and the structure of the Magellanic Stream indicate they might have fallen into our galaxy's gravitational influence relatively recently, perhaps within the past few billion years. This ongoing merger process shows how galaxies grow through the accretion of smaller systems. The Andromeda Galaxy looms large in our cosmic future. This massive spiral galaxy contains roughly 1 trillion stars and is approaching us at about 110 kilometers per second. In approximately 4.5 billion years, Andromeda and the Milky Way will collide and merge, creating a new elliptical galaxy that astronomers have nicknamed Milkomeda. Computer simulations of this future merger show that despite the violence of the collision on galactic scales, individual star systems will likely remain intact. The distances between stars are so vast that direct stellar collisions will be extremely rare. Instead, gravitational interactions will scatter stars into new orbits, transforming both galaxies from organized spirals into a chaotic elliptical system. Our solar system has roughly a 12% chance of being ejected from the merged galaxy during this collision. If this happens, we'll become residents of intergalactic space, watching the merger continue from a distance of hundreds of thousands of light years. The night sky, from such a vantage point, would be spectacular, with the merged galaxy appearing as a brilliant cloud of light, slowly evolving over millions of years. The cosmic web provides the largest scale context for understanding our place in the universe. Galaxies aren't randomly distributed through space, but instead follow filaments of dark matter that connect massive nodes where galaxy clusters form. Our local group sits at the intersection of several such filaments, which channel gas and smaller galaxies toward us over cosmic time. The Virgo cluster, containing over 1,300 galaxies, lies roughly 54 million light-years away and represents the nearest major concentration of galaxies. Our local group is slowly falling toward Virgo, though we'll never reach it due to the accelerating expansion of the universe driven by dark energy. We exist in a cosmic watershed, gravitationally bound to our local environment, but forever separated from more distant structures. The cosmic microwave background radiation provides a snapshot of the universe when it was just 380,000 years old, revealing the tiny density fluctuations that would eventually grow into galaxies like our own. These ancient ripples in space-time detected by missions like Planck and WMAP show that our galaxy formed from a slight overdensity in the primordial universe, a cosmic seed that was just 1 part in 100,000 denser than average. From this humble beginning, gravity slowly assembled the first stars and galaxies over hundreds of millions of years. Our Milky Way likely formed through the merger of smaller proto-galactic fragments, each contributing stars, gas, and dark matter to the growing system. The oldest stars in our galaxy's halo preserve chemical signatures from this chaotic assembly period, when the universe was much younger and more violent than today. The reionization epoch, when the first stars and galaxies began shining and ionizing the neutral hydrogen that filled the early universe, marks a crucial transition in cosmic history. Our galaxy's most ancient stars formed during or shortly after this period, making them witnesses to one of the most dramatic transformations in cosmic evolution. These stellar fossils carry information about conditions in the early universe that we can't obtain any other way. Population 3. Stars, the very first generation of stars in the universe, contained no elements heavier than lithium. These massive, short-lived giants burned through their nuclear fuel in just a few million years before exploding as supernovae, enriching the universe with the first heavy elements. None of these primordial stars survive today, but their chemical signatures might be preserved in the most metal-poor stars we observe in our galaxy's halo. The search for Population 3 survivors continues with surveys like the Pristine Survey and the Hamburg ESO survey, which use specialized techniques to identify extremely metal-poor stars. These ancient objects with iron abundances less than 1/10,000th that of our Sun provide direct links to the earliest epochs of stellar evolution and galactic chemical enrichment. Our galaxy's assembly history can be read in the ages and chemical compositions of its stellar populations. The thick disk formed early and rapidly within the first few billion years after the Big Bang, while the thin disk where we reside assembled more gradually over the galaxy's entire lifetime. This inside-out growth pattern is common among spiral galaxies and reflects the way gas cools and settles into rotating disks over cosmic time. The Galactic Archaeological Survey uses the chemical fingerprints of stars to reconstruct our galaxy's merger history. Different stellar populations retain memory of their origins in their elemental abundances, allowing astronomers to identify stars that formed in satellite galaxies before being accreted by the Milky Way. These stellar immigrants make up a significant fraction of our galaxy's halo population. Recent discoveries have revealed that our galaxy experienced a major merger roughly 10 billion years ago with a galaxy astronomers have named Gaia Enceladus. This ancient collision brought roughly 10 billion solar masses of stars and dark matter into our galaxy, significantly affecting its structure and evolution. The disrupted remnants of this merger can still be identified through their distinctive chemical signatures and orbital properties. The concept of galactic cannibalism takes on new meaning when we consider that our galaxy has consumed dozens of smaller systems over its lifetime. Each merger adds mass and complexity to our galactic home while erasing the individual identities of the accreted systems. We're living in a cosmic graveyard filled with the remains of galaxies that no longer exist as separate entities. Stellar archaeology extends beyond our own galaxy to the local group and beyond. The chemical evolution of different galaxies follows distinct paths depending on their mass, star formation history, and merger experiences. By comparing stellar populations across multiple galaxies, astronomers can understand how environment influences galactic evolution and chemical enrichment. The metallicity-luminosity relation shows that more massive galaxies tend to be more metal-rich, reflecting their ability to retain the heavy elements produced by stellar nucleosynthesis. Smaller galaxies lose much of their enriched gas through supernova-driven winds, while larger systems like ours can hold on to their chemical wealth and continue enriching over cosmic time. Dwarf galaxies in our local group serve as laboratories for understanding galactic evolution in low-mass systems. These small galaxies have simpler star formation histories and lower metallicities than major spirals, providing insights into how the first galaxies formed and evolved. Some dwarf galaxies have been quenched, their star formation shut off by environmental effects or internal processes, while others continue forming stars today. The Fornax dwarf galaxy, one of our galaxy's satellites, contains globular clusters that are younger than those in the Milky Way, suggesting a more extended star formation history. This diversity among satellite galaxies reflects the complex interplay between internal evolution and environmental influences in shaping galactic properties over cosmic time. Tidal streams from disrupted satellites create a fossil record of our galaxy's accretion history. The Sagittarius Stream, Orphan Stream, and numerous other stellar rivers flowing through our galaxy's halo tell stories of ancient mergers and ongoing disruption. These streams will eventually fade as their stars disperse throughout the galactic halo, but for now they provide direct evidence of our galaxy's growth through cannibalism. The dark matter substructure predicted by cosmological simulations should contain hundreds of small dark matter halos orbiting our galaxy. Most of these subhalos are too small to form stars and remain completely invisible, but occasionally one might disrupt a stellar stream or perturb the orbits of nearby stars. The search for these dark satellites continues through gravitational effects and gaps in stellar streams. Gravitational microlensing provides another tool for studying dark matter and low-mass objects in our galaxy. When a compact object passes in front of a background star, its gravity acts as a lens, temporarily brightening the star in a characteristic way. These events can reveal brown dwarfs, rogue planets, and potentially even primordial black holes that might make up part of the dark matter. The optical gravitational lensing experiment and other microlensing surveys monitor millions of stars toward the galactic center and Magellanic Clouds, detecting dozens of lensing events each year. These observations have revealed a population of free-floating planets ejected from their birth systems, as well as providing constraints on the amount of dark matter in compact objects. Stellar proper motions measured by Gaia reveal the complex dynamics of our galactic neighborhood. Stars aren't fixed points of light but are constantly moving through space, following orbits determined by the galaxy's gravitational field. Over human timescales, these motions are imperceptible, but over thousands of years, they gradually change the shapes of constellations and the appearance of our night sky. The fastest-moving star in our galactic neighborhood is Barnard's star, a red dwarf located just 6 light-years away that moves across the sky at a rate of 10.3 arc-seconds per year. This might sound tiny, but it's fast enough that the star will move a distance equal to the Moon's diameter in about 180 years. In roughly 10,000 years, Barnard's star will be the closest star to our solar system. High-velocity stars provide clues about galactic structure and evolution. These objects, moving much faster than typical stars in our neighborhood, might have been accelerated by gravitational interactions with massive objects or ejected from disrupted stellar systems. Some high-velocity stars appear to be visitors from the galactic halo, temporarily passing through the disk on highly eccentric orbits. The local standard of rest, defined by the average motion of nearby stars, provides a reference frame for measuring peculiar velocities. Our Sun's motion, relative to this standard, reveals information about our formation environment and subsequent migration through the galaxy. The fact that we're moving faster than average suggests we might have formed closer to the galactic center and migrated outward over time. Radial migration, the process by which stars move to different galactic radii while maintaining roughly circular orbits, can transport stars across vast distances over cosmic time. Resonances with spiral arms and bar structures can gradually change a star's angular momentum, causing it to spiral inward or outward through the galactic disk. This process might explain the chemical diversity observed among stars at any given galactic radius. Our solar system's birth cluster has long since dispersed, its member stars scattered throughout the galaxy, by gravitational perturbations and differential galactic rotation. Identifying our stellar siblings requires careful analysis of ages, chemical compositions, and orbital properties. Several candidate solar siblings have been proposed, but definitive identification remains challenging due to the complex dynamics of stellar motion over billions of years. The galactic habitable zone concept has evolved to include temporal as well as spatial considerations. Early in the galaxy's history, metallicity levels were too low to form terrestrial planets, while the future will see declining star formation rates and increasing stellar radiation as the galaxy ages. We exist during a cosmic sweet spot when conditions are optimal for complex life. Astrobiology considerations extend beyond individual planetary systems to galactic-scale phenomena. The distribution of heavy elements, the frequency of sterilizing events like gamma-ray bursts and supernovae, and the availability of long-lived stars all influence where and when life might arise in our galaxy. Our location and timing appear remarkably favorable for the development of complex, intelligent life. The galactic phosphorus problem illustrates how stellar nucleosynthesis affects the potential for life throughout the galaxy. Phosphorus, essential for DNA and cellular energy storage, is produced primarily in massive stars and distributed through supernova explosions. The buildup of phosphorus in the interstellar medium took billions of years, potentially delaying the emergence of complex life until relatively recently in galactic history. Rare Earth elements, despite their name, are actually more abundant in our solar system than in most stellar environments. These elements, crucial for modern technology and potentially for advanced life, are produced through specific nucleosynthetic processes that vary across the galaxy. Our solar system's composition reflects a fortunate combination of stellar sources and timing that might not be common elsewhere. The anthropic principle suggests that we observe the universe to have properties compatible with our existence precisely because we exist to observe it. Applied to our galactic environment, this principle might explain why we find ourselves in such an apparently favorable location and time. Regions or epochs hostile to life would have no observers to note their properties. However, the anthropic principle remains controversial among scientists. Some argue it's a cop-out that abandons the search for physical explanations, while others see it as a legitimate consideration in a universe that might contain many regions with different properties. The debate touches on fundamental questions about the nature of scientific explanation and our role as observers in the cosmos. The mediocrity principle, in contrast, suggests that Earth and humanity are typical rather than special. If this principle applies, then life should be common throughout the galaxy, arising wherever conditions permit. The apparent absence of obvious signs of extraterrestrial intelligence then becomes a puzzle requiring explanation through factors like the rarity of intelligence, the tendency for civilizations to destroy themselves, or the difficulty of interstellar communication. Recent advances in astrobiology have expanded our understanding of life's potential in extreme environments. Extremophiles on Earth thrive in conditions once thought impossible for life, from the deep ocean to highly radioactive environments. These discoveries suggest that the galactic habitable zone might be much larger than previously thought, encompassing a wider range of stellar and planetary environments. The concept of planetary protection takes on galactic significance when we consider the potential for life to spread between worlds through natural processes. Meteorite impacts can eject material from planetary surfaces at velocities sufficient to escape gravitational wells, potentially carrying microorganisms to other worlds. Over galactic timescales, this panspermia process might distribute life throughout our stellar neighborhood. The galactic magnetic field represents one of the most pervasive yet invisible aspects of our cosmic environment. This field, though incredibly weak by terrestrial standards at just a few microgauss, threads through the entire galaxy and plays crucial roles in star formation, cosmic ray propagation, and the behavior of interstellar gas. We're constantly immersed in this galactic magnetic environment, completely unaware of its presence in our daily lives. Radio astronomy has revealed that our galaxy's magnetic field follows the spiral arm structure, creating a complex pattern that astronomers describe as resembling a cosmic pinwheel. The field lines are twisted and tangled by differential rotation. The fact that different parts of the galaxy rotate at different speeds. This creates a magnetic field structure that has taken billions of years to develop and continues evolving today. Cosmic rays, high-energy particles accelerated by supernova shockwaves and other violent processes, are trapped and guided by these magnetic field lines. Without the galactic magnetic field, cosmic rays would stream directly out of the galaxy, but instead they're confined for millions of years, bouncing back and forth along field lines like pinballs in a cosmic machine. This confinement allows cosmic rays to interact with interstellar gas and contribute to the heating and ionization of the galactic medium. The cosmic ray flux at Earth varies with our position in the galaxy and our motion through different magnetic field regions. As our solar system orbits the galactic center, we encounter regions with different cosmic ray densities and magnetic field strengths. Some scientists have proposed that these variations might influence Earth's climate through effects on cloud formation, though this remains a topic of active research and debate. Pulsar observations provide some of our best tools for mapping the galactic magnetic field. These rapidly spinning neutron stars emit beams of radio waves that are affected by magnetic fields along their paths to Earth. By measuring the polarization and dispersion of pulsar signals, astronomers can reconstruct the three-dimensional structure of magnetic fields throughout our galactic neighborhood. The discovery of magnetars, neutron stars with magnetic fields, quadrillions of times stronger than Earth's, has revealed the extreme end of magnetic field physics in our galaxy. These objects occasionally produce giant flares that release more energy in a tenth of a second than our Sun produces in a year. A magnetar flare occurring within a few thousand light-years of Earth could potentially affect our planet's atmosphere and technological systems. Magnetic reconnection events in the galactic magnetic field might create regions of enhanced particle acceleration and energy release. These cosmic magnetic storms, similar to solar flares but on galactic scales, could contribute to the high-energy phenomena we observe throughout the galaxy. The complex topology of the galactic magnetic field creates numerous opportunities for such reconnection events. The interstellar medium exists in multiple phases with vastly different temperatures and densities. Cold molecular clouds with temperatures of just 10 to 20 Kelvin coexist with hot ionized gas at temperatures exceeding 1 million Kelvin. These phases are in constant interaction, with supernova explosions creating hot bubbles that expand and cool, while gravitational collapse creates new, cold, dense regions. Superbubbles, vast cavities blown out by multiple supernova explosions, can grow to hundreds of light-years in diameter. These structures, filled with million-degree gas, represent some of the most energetic phenomena in the galactic disk. The local bubble, which contains our solar system, is one such superbubble created by supernova explosions over the past 10 to 20 million years. The three-phase model of the interstellar medium describes how these different phases coexist and interact. Cold neutral medium, warm neutral medium, and hot ionized medium each occupy different fractions of the galactic volume and contribute differently to the overall dynamics of gas flow and star formation. We're currently traveling through the interface between these phases in a region where hot and warm gas mix. Turbulence in the interstellar medium creates a complex, ever-changing structure that affects star formation and galactic evolution. This turbulence is driven by supernova explosions, stellar winds, and gravitational instabilities, creating a chaotic environment where gas flows and eddies on scales ranging from astronomical units to hundreds of light years. Understanding this turbulence is crucial for predicting where and when new stars will form. The galactic fountain model describes how gas cycles between the disk and halo of our galaxy. Hot gas heated by supernova explosions rises out of the galactic plane, cools as it expands, and eventually falls back down as cooler clouds. This circulation pattern helps regulate star formation and distributes heavy elements throughout the galaxy over cosmic time. High-velocity clouds, mysterious concentrations of neutral hydrogen moving at speeds that don't match galactic rotation, might represent part of this galactic fountain or infalling material from intergalactic space. These clouds, some containing millions of solar masses of gas, provide fresh fuel for star formation and help maintain the galaxy's gas supply over billions of years. The Smith cloud, a high-velocity cloud containing roughly 1 million solar masses of gas, is currently plunging toward our galactic disk at over 200 kilometers per second. When it impacts the disk in roughly 30 million years, it will trigger a burst of star formation and add to the galaxy's mass. This ongoing accretion of gas helps explain how spiral galaxies like ours maintain their star formation rates over cosmic time. Stellar feedback processes regulate star formation throughout the galaxy by heating and dispersing the gas from which stars form. Massive stars produce powerful stellar winds that can clear out entire star-forming regions, while supernova explosions inject enormous amounts of energy into the surrounding medium. This feedback creates a self-regulating system where star formation rates adjust to maintain a rough balance between gas consumption and replenishment. The Kennicutt-Schmidt law describes the relationship between gas density and star formation rate in galaxies. This empirical relationship, observed in our galaxy and others, shows that star formation efficiency increases with gas density, but never becomes perfectly efficient. Most of the gas in molecular clouds is dispersed rather than converted into stars, limiting the rate at which galaxies can form new stellar populations. Stellar associations and OB associations represent the most massive star-forming regions in our galaxy. These loose groupings of young, hot stars are gradually dispersing due to their internal motions and the disruptive effects of stellar evolution. The Scorpius-Centaurus association, the nearest OB association to our solar system, contains hundreds of massive stars spread across hundreds of light years. The life cycle of stellar associations provides insights into how star formation proceeds and how stellar feedback affects subsequent generations of star formation. Young associations are compact and gas-rich, but stellar winds and supernova explosions gradually clear out the remaining gas and disperse the stellar population. Eventually, only the longest-lived stars remain as a sparse, moving group. Wolf-Rayet stars, massive evolved stars that have shed their outer hydrogen layers, represent one of the most extreme phases of stellar evolution in our galaxy. These objects produce powerful stellar winds moving at thousands of kilometers per second, creating spectacular nebulae and contributing significantly to the chemical enrichment of the interstellar medium. Our galaxy contains only a few hundred known Wolf-Rayet stars, making them among the rarest stellar types. The WR140 ring nebula, created by the interaction between a Wolf-Rayet star's wind and the surrounding interstellar medium, spans over 100 light-years and represents one of the largest stellar wind bubbles known. These structures show how individual massive stars can affect their environments on scales comparable to entire star-forming regions. Luminous blue variables represent another extreme phase of massive stellar evolution. These unstable giants undergo dramatic eruptions that can temporarily make them among the brightest stars in the galaxy. Eta Carinae, the most famous example in our galaxy, ejected several solar masses of material during its great eruption in the 1840s, creating the spectacular homunculus nebula visible today. The rarity of these extreme stellar phases highlights how special massive stars are in galactic evolution. While they represent less than 1% of all stars by number, massive stars dominate the energy output, chemical enrichment, and structural evolution of galaxies. Their short lifetimes mean they remain close to their birthplaces, creating a strong correlation between current star formation and the locations of these stellar giants. Binary star evolution adds another layer of complexity to stellar populations in our galaxy. Roughly half of all stars exist in binary or multiple systems where gravitational interactions can dramatically alter their evolutionary paths. Mass transfer between binary components can create exotic objects like X-ray binaries, cataclysmic variables, and Type Ia supernovae. X-ray binaries, where a compact object accretes material from a companion star, represent some of the most energetic phenomena in our galaxy. The gravitational energy released as material spirals into a neutron star or black hole can outshine entire star clusters, creating brilliant X-ray sources visible across the galaxy. Our galaxy contains hundreds of known X-ray binaries, each representing a unique laboratory for studying matter under extreme conditions. Cataclysmic variables, binary systems containing white dwarf stars that periodically undergo thermonuclear explosions on their surfaces, contribute to the chemical evolution of the galaxy through nova explosions. These events, which can temporarily increase a star's brightness by factors of millions, help distribute elements like lithium, carbon, and nitrogen throughout the interstellar medium. Type Ia supernovae, the thermonuclear explosions of white dwarf stars in binary systems, serve as both cosmic distance indicators and major sources of iron peak elements. These explosions are remarkably uniform in their properties, making them crucial tools for measuring cosmic distances and studying the expansion history of the universe. Our galaxy experiences roughly one Type Ia supernova every few hundred years. The double degenerate scenario for Type Ia supernovae involves the merger of two white dwarf stars, while the single degenerate scenario involves a white dwarf accreting material from a normal companion until it reaches the critical mass for thermonuclear explosion. Recent observations suggest both channels might contribute to the Type Ia supernova rate in our galaxy. Gravitational wave astronomy has opened a new window on binary evolution in our galaxy. The LIGO and Virgo detectors have observed dozens of mergers between black holes and neutron stars, revealing a population of compact binary systems that were previously invisible. These observations provide direct evidence for the final stages of massive binary evolution. The merger rate of compact binaries in our galaxy appears to be higher than previously expected based on pulsar observations alone. This suggests that many binary systems evolve through channels that don't produce observable pulsars, highlighting the complexity of binary stellar evolution and the importance of gravitational wave observations for understanding stellar populations. Stellar remnants, white dwarfs, neutron stars, and black holes represent the endpoints of stellar evolution and provide fossil records of past star formation in our galaxy. The white dwarf luminosity function, which describes the number of white dwarfs at different brightness levels, provides an independent measure of the star formation history in our galactic neighborhood over the past 10 billion years. The coolest white dwarfs in our galaxy have surface temperatures of just a few thousand Kelvin and ages approaching the age of the universe itself. These ancient stellar remnants formed when the galaxy was young and metal-poor, providing direct links to the earliest epochs of stellar evolution. Their existence proves that low-mass stars formed throughout galactic history, not just in recent times. Neutron star populations reveal information about the high-mass end of stellar evolution and the supernova rate throughout galactic history. The known pulsar population represents only a small fraction of the total neutron star population, since pulsars are only visible when their beams sweep across Earth and only remain active for a few million years after formation. The galactic neutron star population might exceed 100 million objects, most of them invisible and undetectable with current technology. These stellar corpses drift through the galaxy like cosmic ghosts, occasionally revealing their presence through gravitational effects or rare interactions with other objects. The nearest neutron star might be closer than the nearest normal star, yet remain completely invisible to our instruments. The stellar mass black hole population in our galaxy represents perhaps the most mysterious component of stellar remnants. Current estimates suggest our galaxy contains roughly 100 million stellar mass black holes, yet we've only directly detected a few dozen through their interactions with companion stars or gravitational wave emissions. These invisible monsters drift through space, detectable only when they actively feed or merge with other compact objects. The nearest known black hole, Gaia BH1, lies just 1,500 light-years away, practically next door in galactic terms. This 10 solar mass object was discovered through its gravitational effects on a companion star, highlighting how black holes can hide in plain sight throughout our galactic neighborhood. There might be thousands of similar systems waiting to be discovered as our observational techniques improve. Intermediate mass black holes with masses between stellar and supermassive black holes remain among the most elusive objects in our galaxy. These hypothetical objects, weighing hundreds to thousands of solar masses, might form through runaway stellar collisions in dense star clusters or represent the seeds from which supermassive black holes grow. Despite decades of searching, confirmed intermediate mass black holes remain frustratingly rare. The supermassive black hole at our galactic center, Sagittarius A star, weighs roughly 4 million solar masses and sits 26,000 light-years away. This cosmic monster influences the orbits of stars throughout the galaxy, yet it's currently quite peaceful, accreting material at a rate that produces relatively little radiation. The Event Horizon Telescope's image of this black hole in 2022 marked a historic achievement in astronomy. The galactic center region represents one of the most extreme environments in our galaxy. Stars there experience gravitational fields billions of times stronger than what we experience on Earth, while the density of stellar objects exceeds that of our solar neighborhood by factors of millions. Some stars orbit so close to Sagittarius A star that they complete full orbits in just 16 years, reaching speeds of several percent the speed of light. S stars, the population of young, massive stars orbiting close to the galactic center, shouldn't exist according to conventional star formation theories. The intense tidal forces near the supermassive black hole should prevent gas clouds from collapsing to form new stars. Their presence suggests either exotic formation mechanisms or that these stars migrated inward from more distant regions through gravitational interactions. The discovery of G-objects near the galactic center has revealed a new class of astronomical phenomena. These objects appear stellar when distant from the black hole, but become extended and dusty during their closest approaches. They might represent stars surrounded by dusty envelopes, or possibly the remnants of stellar mergers triggered by the extreme gravitational environment. Stellar dynamics near supermassive black holes create unique laboratories for testing general relativity and studying matter under extreme conditions. The orbit of the star S2 around Sagittarius A star provided the first direct test of Einstein's theory in the strong field regime, confirming relativistic effects like gravitational redshift and orbital precession with unprecedented precision. The galactic center, GeV excess, a mysterious source of high-energy gamma rays emanating from the central regions of our galaxy, might represent evidence for dark matter annihilation or an unknown population of pulsars. This excess emission, discovered by the Fermi Gamma Ray Space Telescope, has sparked intense debate about its origin and implications for particle physics and astrophysics. Fermi bubbles, enormous structures extending 50,000 light-years above and below the galactic plane, represent evidence for past activity from our galaxy's central black hole. These gamma-ray emitting bubbles, discovered in 2010, suggest that Sagittarius A star was much more active in the recent past, possibly undergoing a period of rapid accretion that created powerful jets and outflows. The nuclear star cluster surrounding our galactic center contains roughly 25 million stars packed into a region just a few light-years across. This represents one of the densest stellar environments in the galaxy, where stellar collisions and close encounters occur much more frequently than in our solar neighborhood. The cluster's properties provide insights into how stars behave in extreme gravitational environments. Hypervelocity stars, objects moving fast enough to escape the galaxy entirely, are thought to originate primarily from gravitational interactions near the galactic center. The Hill's mechanism, where a binary star system is disrupted by the supermassive black hole, can accelerate one star to speeds exceeding 1,000 kilometers per second, while the other is captured into a tight orbit. The discovery of hypervelocity stars throughout the galactic halo provides direct evidence for violent processes occurring near supermassive black holes. These stellar refugees carry information about conditions in the galactic center and serve as probes of the galaxy's gravitational potential. Some hypervelocity stars might even escape the galaxy entirely, becoming intergalactic wanderers. The Milky Way's satellite galaxy system provides crucial context for understanding our place in the cosmic hierarchy. Our galaxy hosts at least 59 known satellite galaxies, ranging from the large Magellanic Cloud with its 10 billion stars down to ultra-faint dwarfs containing just a few thousand stars. This satellite population represents a fossil record of galactic assembly and hierarchical structure formation. The missing satellite problem highlights discrepancies between theoretical predictions and observations of dwarf galaxy populations. Cold, dark matter simulations predict hundreds of satellite halos around galaxies like ours, yet we observe far fewer luminous satellites. This might indicate that most small, dark matter halos failed to form stars, or that observational selection effects prevent us from detecting the faintest systems. Ultra-faint dwarf galaxies discovered in large numbers over the past 2 decades represent the smallest and most dark matter-dominated galaxies known. These systems contain just a few hundred to a few thousand stars spread across hundreds of light-years, making them incredibly difficult to detect despite being relatively nearby. They provide unique laboratories for studying dark matter physics and early galaxy formation. The Magellanic Stream, a trail of gas extending over 100 degrees across the sky, represents ongoing tidal disruption of our galaxy's largest satellites. This stream contains roughly 2 billion solar masses of neutral hydrogen and traces the orbital history of the Magellanic Clouds over the past few billion years. The stream will eventually be accreted by our galaxy, adding to its gas reservoir and triggering future star formation. Stellar streams from disrupted globular clusters and dwarf galaxies create a complex web of tidal debris throughout our galactic halo. The Sagittarius Stream, Orphan Stream, and dozens of other stellar rivers preserve information about past merger events and the gravitational potential of our galaxy. These streams serve as sensitive probes of dark matter distribution and galactic structure. The Gaia mission has revolutionized our understanding of stellar streams and galactic archaeology. By measuring precise positions and motions for over 1 billion stars, Gaia has revealed numerous previously unknown streams and provided detailed maps of known structures. This data allows astronomers to rewind the clock and reconstruct the merger history of our galaxy with unprecedented precision. Phase space analysis of stellar streams provides powerful constraints on the shape and mass distribution of our galaxy's dark matter halo. The way streams evolve and disperse depends sensitively on the gravitational potential they experience, allowing astronomers to map dark matter structure through its effects on visible tracers. These studies suggest our galaxy's dark matter halo might be more spherical than previously thought. The local group's dynamics reveal the influence of dark matter on the largest scales accessible to detailed study. The relative motions of the Milky Way, Andromeda, and Triangulum galaxies depend on the total mass and distribution of dark matter throughout the group. Precise measurements of these motions provide independent estimates of the local group's total mass and dark matter content. Timing arguments based on the current separation and relative velocity of the Milky Way and Andromeda suggest the local group has a total mass of roughly 5 trillion solar masses, with dark matter comprising about 85% of this total. This mass estimate agrees well with other methods, providing confidence in our understanding of dark matter's role in galactic dynamics. The cosmic web's influence extends down to galactic scales through the accretion of gas and small galaxies along dark matter filaments. Our local group sits at the intersection of several such filaments which have channeled material toward us over cosmic time. This ongoing accretion helps explain how galaxies maintain their gas supplies and continue forming stars over billions of years. The zone of avoidance, the region of sky obscured by our galaxy's dust and gas, hides roughly 10% of the extragalactic universe from optical observations. Radio and infrared telescopes can peer through this dust to reveal hidden galaxies and large-scale structures, but significant portions of the nearby universe remain poorly mapped due to galactic obscuration. Recent surveys using radio telescopes and infrared space missions have begun to fill in this hidden zone, revealing galaxy clusters and superclusters that were previously unknown. These discoveries affect our understanding of local large-scale structure and the gravitational forces acting on our local group. The Great Attractor, a massive concentration of galaxies partially hidden behind our galactic plane, exerts significant gravitational influence on our cosmic neighborhood. The Shapley supercluster, the largest concentration of galaxies in our local universe, lies roughly 650 million light-years away and contains thousands of galaxies with a total mass exceeding 10,000 trillion solar masses. This enormous structure influences the motion of galaxies across hundreds of millions of light-years, including our own local group's peculiar velocity relative to the cosmic microwave background. Bulk flows, the coherent motion of galaxies over large scales, suggest that our local universe is being pulled toward even more distant mass concentrations. These flows challenge our understanding of cosmic homogeneity and might indicate the presence of massive structures beyond our current observational horizons. The nature and extent of these bulk flows remain active areas of research. The dipole anisotropy in the cosmic microwave background, caused by our motion relative to the cosmic rest frame, reveals that our local group is moving at roughly 600 kilometers per second toward the constellation Hydra. This motion results from gravitational attraction by massive structures in that direction, highlighting how local gravitational fields affect our cosmic trajectory. Our galaxy's motion through the cosmic web creates a bow shock as it plows through the intergalactic medium. This interaction strips gas from our galaxy's outer halo and creates a wake of disturbed material trailing behind us. The ram pressure from this motion might affect star formation in our galaxy's outer regions and influence the properties of our satellite galaxy system. The concept of the galactic year, the time required for our solar system to complete one orbit around the galactic center, provides a natural time scale for galactic evolution. During our Sun's roughly 20 completed galactic years, the galaxy has evolved significantly, accreting satellite galaxies, forming new stellar populations, and gradually changing its structure and composition. Galactic seasons, caused by our oscillatory motion through the galactic plane, expose our solar system to different environments over tens of millions of years. As we move through regions of varying stellar density, gas content, and radiation fields, these changes might influence Earth's climate and biological evolution through mechanisms we're only beginning to understand. The galactic habitable zone concept continues to evolve as we learn more about the factors affecting planetary habitability on galactic scales. Metallicity gradients, supernova rates, stellar densities, and radiation environments all vary with position in the galaxy, creating a complex landscape of habitability that changes over cosmic time. Our current location and timing appear remarkably favorable for complex life. The galactic chemical evolution tells a story written in the very atoms that make up our bodies. Every element heavier than hydrogen and helium was forged in the nuclear furnaces of stars or created in the violent explosions that mark their deaths. The iron in our blood was created in the core of a massive star that exploded billions of years ago. The calcium in our bones was synthesized through silicon burning in stellar cores at temperatures exceeding 3 billion Kelvin. Different stellar processes contribute distinct elemental signatures to the galactic chemical inventory. Alpha elements like oxygen, neon, magnesium, and silicon are produced primarily in massive stars and dispersed through core collapse supernovae. Iron peak elements like iron, nickel, and cobalt come mainly from type Ia supernovae, the thermonuclear explosions of white dwarf stars. Neutron capture elements like gold, platinum, and uranium are created in neutron star mergers and the most extreme supernova explosions. The R process, or rapid neutron capture process, occurs in environments with neutron densities so extreme that atomic nuclei can capture neutrons faster than they can decay. These conditions exist for just seconds during neutron star mergers or certain types of supernovae, yet they're responsible for creating roughly half of all elements heavier than iron. The gold in your jewelry was likely forged in one of these cosmic catastrophes. The S process, or slow neutron capture process, operates in the interiors of evolved stars over thousands of years. Asymptotic giant branch stars, in their final phases of evolution, create elements like strontium, barium, and lead through this gradual neutron capture mechanism. These stars then eject their enriched material through stellar winds, distributing S-process elements throughout the galaxy. Stellar nucleosynthesis operates like a cosmic assembly line, with each stellar generation building upon the work of its predecessors. The first stars in the universe could only create elements up to iron through fusion processes. Subsequent generations inherited these elements and used them to create rocky planets and more complex chemistry. We exist because billions of years of stellar evolution have enriched our corner of the galaxy with the ingredients for life. The metallicity gradient in our galaxy shows how chemical enrichment varies with distance from the galactic center. Inner regions are more metal-rich due to higher rates of star formation and supernova enrichment, while outer regions remain more pristine. This gradient affects planet formation, stellar evolution, and potentially the development of life throughout the galaxy. Our solar system's metallicity places us in the galactic suburbs, where conditions are just right for forming terrestrial planets without the radiation hazards of the inner galaxy. Stars forming today in the galactic center have metallicities several times higher than our Sun, potentially creating super-Earths and planets with compositions unlike anything in our solar system. The age-metallicity relation in our galactic neighborhood shows how chemical enrichment has proceeded over cosmic time. The oldest stars are metal-poor, formed when the galaxy was young and chemically unevolved. Younger stars show progressively higher metallicities, documenting the gradual buildup of heavy elements through successive generations of stellar evolution. Stellar archaeology uses these chemical fingerprints to reconstruct galactic history. Each star preserves the chemical composition of the gas cloud from which it formed, creating a fossil record of past nucleosynthesis and chemical evolution. By analyzing thousands of stars with different ages and origins, astronomers can map the galaxy's chemical evolution in unprecedented detail. The Gala survey, using the Anglo-Australian telescope, has measured chemical abundances for hundreds of thousands of stars throughout our galactic neighborhood. This data reveals the complex history of chemical mixing, stellar migration, and galactic assembly that has shaped our cosmic environment over billions of years. Lithium, the third lightest element, presents one of the most puzzling aspects of galactic chemical evolution. Big Bang nucleosynthesis created a specific amount of lithium in the early universe, but observations of old stars show significantly less lithium than predicted. This lithium problem might indicate unknown stellar processes, exotic particle physics, or gaps in our understanding of primordial nucleosynthesis. Beryllium and boron, created primarily through cosmic ray spallation, the breakup of heavier nuclei by high-energy particles, provide unique traces of galactic cosmic ray history. The abundances of these fragile elements in old stars reveal information about cosmic ray fluxes in the early galaxy and how they've changed over cosmic time. The fluorine abundance in stars traces the contribution of Wolf-Rayet stars and asymptotic giant branch stars to galactic chemical evolution. This reactive element is destroyed in most stellar environments but created in the specific conditions found in these evolved stellar types. Fluorine measurements help astronomers understand the relative contributions of different stellar sources to chemical enrichment. Isotope ratios provide even more detailed information about nucleosynthetic processes and galactic evolution. The ratio of oxygen-16 to oxygen-18, for example, reflects the balance between massive star nucleosynthesis and lower mass stellar contributions. These isotopic signatures can reveal the star formation history and initial mass function in different galactic regions. Pre-solar grains found in meteorites preserve isotopic signatures from individual stars that contributed material to the solar nebula. These microscopic diamonds, silicon carbide crystals, and other refractory materials survived the formation of our solar system and carry direct information about stellar nucleosynthesis in our galactic neighborhood 4.5 billion years ago. The discovery of live radioactive isotopes in deep-sea sediments and lunar samples suggests that nearby supernova explosions have occurred within the past few million years. Iron-60, with a half-life of 2.6 million years, has been detected in multiple terrestrial reservoirs, indicating that our solar system has been exposed to supernova debris in the recent past. These recent supernova explosions might be connected to the local bubble, the low-density cavity in the interstellar medium that currently surrounds our solar system. Multiple supernovae over the past 10 to 20 million years could have carved out this bubble while simultaneously enriching our local environment with fresh nucleosynthetic products. The chemical evolution of our galaxy continues today through ongoing star formation and stellar death. Every supernova explosion adds roughly 1 solar mass of heavy elements to the interstellar medium, while stellar winds from massive stars contribute additional enriched material. This ongoing chemical evolution ensures that stars forming today have higher metallicities than those that formed in the past. Future chemical evolution will depend on the galaxy's gas supply and star formation rate. As the universe ages and cosmic expansion accelerates, galaxies will become increasingly isolated and unable to accrete fresh gas from intergalactic space. Eventually, star formation will decline as gas supplies are exhausted, leading to a gradual cessation of chemical enrichment. The concept of chemical tagging uses detailed abundance patterns to identify stars that formed together but have since dispersed throughout the galaxy. Stars born in the same molecular cloud should have nearly identical chemical compositions, allowing astronomers to reconstruct dissolved stellar associations and star formation history even billions of years after the original clusters have dispersed. Galactic archaeology extends beyond our own galaxy to the local group and beyond. Different galaxies have followed distinct chemical evolution paths depending on their mass, star formation history, and environmental influences. Dwarf galaxies, with their lower masses and episodic star formation, show different abundance patterns than massive spirals like our own. The chemical evolution of the Magellanic Clouds reveals the effects of tidal interactions and ram pressure stripping on smaller galaxies. These systems have lost significant amounts of gas through their interactions with our galaxy, affecting their ability to retain the products of stellar nucleosynthesis and continue chemical enrichment. Stellar migration complicates the interpretation of chemical gradients and abundance patterns in our galaxy. Stars don't remain at their birth radii, but can migrate significant distances through gravitational interactions with spiral arms, molecular clouds, and other stellar systems. This radial mixing helps explain the chemical diversity observed among stars at any given galactic location. The thick disk of our galaxy shows distinct chemical signatures compared to the thin disk where we reside. Thick disk stars are enhanced in alpha elements relative to iron, suggesting they formed during a period of rapid star formation when massive stars dominated the chemical enrichment. This population might represent the remnant of an ancient starburst or merger event. Chemical evolution models attempt to reproduce the observed abundance patterns through detailed simulations of star formation, stellar evolution, and gas dynamics. These models must account for the complex interplay between stellar nucleosynthesis, supernova feedback, gas inflows and outflows, and stellar migration to match the chemical diversity we observe. The yields of different stellar types, the amounts of various elements they produce and eject, remain uncertain for many nucleosynthetic processes. Theoretical calculations of stellar evolution and nucleosynthesis must be calibrated against observations of stellar abundances and supernova remnants to improve our understanding of how stars enrich the galaxy. Galactic chemical evolution connects to astrobiology through its effects on planetary composition and habitability. The carbon-to-oxygen ratio in stellar atmospheres affects the types of planets that can form, with carbon-rich systems potentially creating carbide planets rather than silicate worlds like Earth. The abundance of volatile elements affects atmospheric composition and the potential for liquid water. The galactic sulfur anomaly, the observation that sulfur abundances don't follow the same trends as other alpha elements, highlights gaps in our understanding of stellar nucleosynthesis and chemical evolution. This discrepancy might indicate unknown stellar processes or systematic errors in abundance measurements, demonstrating that galactic chemical evolution remains an active area of research. Hypervelocity stars provide unique laboratories for studying chemical evolution because they sample stellar populations from throughout the galaxy. These high-speed stellar refugees, ejected from the galactic center or other regions, carry chemical information about their birth environments to distant parts of the galactic halo where they can be studied in detail. The chemical evolution of globular clusters reveals how stellar populations evolve in isolation from the galactic chemical evolution. These ancient stellar systems show evidence for multiple generations of stars with different chemical compositions, suggesting that massive clusters can undergo their own internal chemical evolution through the pollution of successive stellar generations. The future of galactic chemical evolution will be shaped by the ongoing merger with the Andromeda Galaxy. This collision will trigger intense star formation and mix stellar populations with different chemical histories, creating a new galaxy with a complex chemical structure that reflects the merger process. The chemical signatures of this event will be preserved in stellar abundances for billions of years. If you made this far, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. This is why we will never leave the Milky Way. Learn how the expansion of the universe, dark energy, and the cosmic event horizon put most galaxies forever out of reach, and why even the most advanced propulsion concepts can't overcome the fundamental laws of physics. See you there.